Part two, moving on to page two, we're going to talk about mechanical energy. So mechanical energy basically includes all of your potential energies. So this would include your spring potential energy as well as your gravitational potential energy, plus kinetic energy. So it's the sum of all of the kinetic and potential energies. So if we have no change in mechanical energy, it is said that the mechanical energy is conserved. So typically when this happens is when we have no dissipative forces, meaning there's no dissipated energy. That would be the only case where mechanical energy would not be conserved, is if there's any kind of external force beyond that, like some kind of applied force that's kind of adding things to it, or you have some kind of frictional force that's acting to kind of remove energy from the system. So that's when it would not be conserved. And we'll do plenty of examples as we go along with that to see when it is and is not conserved. So talking about that conservation of mechanical energy, it is really a subset of conservation of energy because energy is always conserved. But when we look at just the mechanical energy, if we have some external forces or we have friction acting here, then it would not be conserved. It's kind of a tricky thing when asked the question, is the mechanical energy conserved? Because it really depends on how the system is defined for you. And again, we're going to be doing a lot of examples on this, but this is really just to alert you to the fact that we really need to kind of pay attention to how the system is getting defined for us. So let's look at a couple of examples where we're looking at this conservation of mechanical energy, yes or no for that. So first, we're going to look at an example of just like a ball falling through the air. So if we kind of look at our visual over here, we have the ball. It starts at some initial y position and it has some velocity. And then sometime later, it's at some new final y position. And we can see we have a much bigger velocity because it's accelerating forward. So when we look at the closed versus the open system, look at how the system is defined. In this first case, we're going to include the Earth plus the ball as our system. And in the open system, we're just going to look at the object of interest, just the ball. So let's kind of look at what that means as far as that perspective. So if the system includes the Earth plus the ball, this is telling me that I'm going to include gravitational potential energy because that's where that energy is stored, plus any kind of kinetic energy. So a nice model for this is we use bar graphs to kind of model. It's kind of the equivalent of a force diagram from forces to energy. So if we kind of start with our gravitational potential energy and kinetic energy, the ball is moving. So I'm going to give it like one box of energy. So again, just kind of a random representation of how much energy it has. And the ball is kind of located some big distance, some y initial distance above the ground. So I'm going to give it like 4 boxes of gravitational potential energy. So yeah, we'll count out 4 boxes. So the total amount of energy, my total mechanical energy in this system is going to be 5 boxes of energy. So 1, 2, 3, 4, 5. So this would be kind of at y equals y initial. That would be my initial location. Then after a while, it's going to fall closer to the ground. And again, some of this gravitational potential energy has been transformed into kinetic energy. So as it falls lower and lower, it's going to lose some of that gravitational potential energy. So I'm going to give it, I don't know, I'll give it like 2 boxes of gravitational potential energy. Again, these are not to scale or anything. I'm just kind of making it, showing that I'm decreasing my gravitational potential energy because I'm getting closer to the ground. So my mechanical, if there's no air resistance, my mechanical energy is conserved. So I still need to have 5 boxes of energy. So if I've kind of lost 2 boxes of gravitational potential energy, that has been transformed into kinetic energy. So now I'm going to have 2 boxes over here. So I'll have a total of 3 boxes of kinetic energy. I still have the same 5 units or boxes of total mechanical energy, and mechanical energy would be conserved. So when we look at how this has been conserved, we're going to have some initial gravitational potential energy plus some initial kinetic energy, and that's going to be equal to some final gravitational potential energy plus the final kinetic energy. It's just kind of writing my boxes into a bit of an equation form. So if I kind of put the gravitational potential energies on one side of the equation, so move this over here, and I take this and move that over here, I'm going to get a very important relationship. So I'm just going to write it all out. Say, oops, I want to go back to my pen. Sorry about that. My initial gravitational potential energy minus my final gravitational potential energy is going to equal my final kinetic minus my initial kinetic energy here. If we remember that the change in something is always final minus initial, we can see that left side of the equation here is a negative change in gravitational potential energy. So negative, oops, let me go back to my pen. Negative change in gravitational potential energy. And then over here, I see final minus initial. That's going to be equal to the change in kinetic energy. So this is a kind of a really important relationship that basically says, however much gravitational potential energy I lose or gain is going to be equal to the gain or loss of kinetic energy. So if this side goes down, that side's going to go up, and the mechanical energy gets conserved. So that's kind of looking at a closed system with conservation of mechanical energy. All right, now if we look at the system where is just the ball, if I look at that same initial position, so my initial position is y is going to be y initial, I'm just going to have one box of kinetic energy in my whole system. But now work is being done by an external force of gravity. So work is done by the gravitational force to add energy to the system. How much energy or how much work is done by gravity? So the work done by gravity is essentially going to be equal to 4 boxes of energy. So at the end of, I'm sorry, not 4 boxes, 3 boxes. My bad. 3 boxes. No, wait, what did I do? Oh my gosh, I messed that up. I'm sorry. And I don't want to start over again to make this video perfect, but please just trust I'm like having a little trouble here. 2 boxes, because I want to make it consistent with what we're doing, right? So the work done by gravity is going to be equal to the 2 boxes of energy. So I'm going to end up with the same 3 boxes of kinetic energy that I had over here. I'm still losing the same 2 boxes as I did in the closed system. It's just a different way to look at it. And then the ultimate answer would say is mechanical energy is not conserved, because my total mechanical energy initially was just 1 box of kinetic energy, and then I finished with, and this should really look like 3 boxes. Geez, I'm really messing this up. This should look like 3 boxes of kinetic energy here. So my mechanical energy would not be conserved because work was done by an external force, specifically gravity, to add energy to the system. So again, that's a lot to take in. And it's a very simple example, but it is such an important feature of understanding the difference between an open system and a closed system. All right, we are going to get started with some of these equations. Again, we are going to focus on the closed system initially, and then we'll head over to the open systems a little bit in a few days, probably 3 or 4 more days from now. All right, so this also should be a bit of a review. This is just getting started with equations. So the kinetic energy equation, if you remember from freshman year, I'm getting my marker again, kinetic energy is going to be equal to 1/2 the mass of the object times the speed squared. We do use V here, and again, we typically associate with velocity, but again, it does not have direction here, and we square it, so there really is no positive or negative direction with it. Just again, reminder, this is a scalar quantity, so we don't have a direction piece associated with it. So this is kind of the instantaneous kinetic energy. And it depends on how big the object is and how fast it's moving. So for constant acceleration, if you recall, the v squared was going to be proportional to twice the acceleration times the change in position. So some connections here, if we see, oh, that should say v squared, not x squared. Boy, I'm really messing up today. So if we kind of look at relationships with constant kinetic energy, we can connect this idea that the kinetic energy, which is proportional to the velocity squared, is also going to be proportional to the displacement, which is also going to be proportional to the acceleration. So we can look at relationships between variables. Kinetic energy is going to go as the square of the speed. Kinetic energy goes linearly with displacement, and kinetic energy is proportional to the acceleration of the system. So just looking at some kind of relationships between variables there and kinetic energy. So again, proportional reasoning, think proportional reasoning. All right, gravitational potential energy. So at any moment in time, gravitational potential energy is basically measured relative to an initial, not an initial, that's not a good word, to an initial, oh gosh, I'm not using the right words again. Basically, we can set our 0 point. Where do we decide that gravitational potential energy is equal to 0? So we have to kind of pick a 0 point. And this is very much user defined. And we can choose where gravitational potential energy is equal to 0 based on convenience, what makes a problem very easy to solve for. So, typically we might choose the ground to be gravitational potential energy, but we'll talk a little bit about pro tips with gravitational potential energy, since I've already kind of messed up this idea of kind of setting that gravitational potential energy equal to 0 someplace. Anyway, the equation, which is probably more important here. Hopefully you skipped over a little bit of that. Gravitational potential energy is going to be equal to the mass of the system times the gravitational field strength. So again, we should recognize this as the weight here, and then the height. The height on your equation sheet, you'll see a y used. Sometimes you'll see h used for height. That's also common, but this is how it's seen on the equation sheet. We'll see it as mgy. All right. So when we start looking at problem solving for, again, isolated systems here, we're going to have this is another word for a closed system here. We need to have some strategies, especially when dealing with gravitational potential energy, because it can be a little bit tricky. So nature is only interested in change. So we can make our gravitational potential energy to be some constant value. But if there's no change in it, it doesn't go up or down, then we're really not super interested in it, because it's not causing any change. It's not transferring into kinetic energy. So we can set gravitational potential energy to be 0 at any convenient point. And I tried to mention that kind of previously, and I kind of butchered that a little bit. But typically, we're going to choose the lowest possible point to be gravitational potential energy equal to 0. So this will come up when we talk a little bit about pendulums in a second here. But if I have a pendulum swinging here above the ground, my pendulum kind of disappeared. Let me draw a picture here. I have a pendulum that's swinging across the ground, and this is the ground level. Because the lowest possible point is going to be at the bottom of the swing, I'll probably want that to be my gravitational potential energy equal to 0, not the ground itself, because this just kind of gives us an offset. So that's an example of making choosing a convenient point for my gravitational potential energy equal to 0. All right, here's another thing that's important. Gravitational potential energy can even be negative. In fact, that when we get back into talking about orbits and things, it'll be negative all the time. So we need to make sure that it can be negative. Again, it's all about the relative changes we have, and we can make 0 to be anywhere. So we could start at a negative value and increase to 0, or we could start at 0 and increase to some positive value. But either way, it's really all about the change, because if you remember, any kind of change, whether it's positive or negative, change is going to be equal to a negative or positive increase in the kinetic energy. So again, it's all about the change is what we want to work on. And then the second thing is that its path. When something changes its location in a gravitational field, it's important to recognize this scalar nature of gravitational potential energy, that it's independent, and only the change in the vertical position is going to matter. So if we kind of look at an example of that, if I have kind of position A here, and I go to position B, if I'm calculating the change in gravitational potential energy, again, here's my ground level here, This is my change in gravitational potential energy right there. What is my change in vertical position? I could go kind of in a straight line path here, or I could take some curlicue path and end up there, or I could go all the way up and come back down here, and it still would have the same change in vertical position regardless of how I got there. So in that case, it kind of gives it that sense of the scalar nature of gravitational potential energy. All right, that finishes up this part of the video.